சொல்லி ஒன்று செய்யக்கூடாது சார் அவர்கள் சொல்லி செய்யக்கூடாது தலையை ஆட்டக்கூடாது. So good morning everyone. I welcome everyone for the 6th day of the Gyan course, the lecture number 16. The title of today's presentation is Ammonia Fuel Cells, Principles and Applications. So learning objectives. So what is the objective of this presentation? So we must know the basic knowledge about the fuel cells. So what are all the components that are associated with the fuel cells? How the fuel cells differs from the battery? Then what is the fundamental difference about the in general combustion with the fuel cell? Understanding fundamentals of ammonia fuel cells and the role in clean energy in comparison with other type of the fuels which can be used for fuel cells. Examine the electrochemical principles behind ammonia as fuel. Discuss key applications of ammonia fuel cells in sustainable transportation and power generation. So the learning overview at the end of the presentation, you may have some idea about, I can say, what is ammonia fuel cell. So what is the electrochemical principle? How the ammonia is used as a fuel in fuel cell? What are the benefits and challenges? Applications in transportation and energy storage. Environmental and economic implications of bringing ammonia fuel cell in comparison with other type of fuels. So as you all know that the fuel cell, so fuel cell, the topic itself, it has a meaning. So the topic fuel cell. So we need fuel and you need a cell. So typically the fuel what we are using in the fuel cell is hydrogen. And currently there are a lot of researches going on in fuel cell in using ammonia. I can say ammonia and methanol. Then hydrocarbon, also direct usage of hydrocarbon in the fuel cell also, lot of research is going on. Fuel cell contains the main important components like, I can say, electrodes, gas, anode, cathode, electrolyte, then we can some type of fuel cell we are bringing the name called gas DDI, gas diffusion. Okay. Then the catalyst. Catalyst for anode, catalyst for cathode, Then catalyst for, I can say, the diffusion. Then we need to produce the electricity. So electricity associated components also part of the yes. So fuel cell differ from conventional cells in respect that active material, fuel and oxygen are not contained in the cell but are supplied from outside. Okay. So in the fuel cell, ultimately we are going to produce electricity in the form of milliamps per unit square area with respect to the fuel cell surface. So in the fuel cell, it has chamber in which you need a provision to keep anode. We need to keep the provision to keep the cathode. Then we have the separation layer, which is going to allow only the positive ions. So before this is nothing but a membrane. Nothing but a membrane. Then you need to coat the catalyst over this to split the hydrogen into H plus and electron minus. Here you have this is the chamber where oxidation reactions happens. Oxidize the fuel. The cathode is the part where the reduction reactions happens. The reduction reactions happens. So normally the hydrogen comes from the surrounding, enters into the chamber where anode is there, where hydrogen is converted into H plus and electron minus. We are going to permit the purpose of the electrolyte going to be available in between anode and cathode. Is used to permit only the positive ions towards the cathode. So only H plus. H plus alone transfer to the cathode side. So during the oxidation process, some amount of heat will be generated. So fuel cell is an electrochemical process in general. Along with oxidation, you are producing H plus electron, then the heat also coming out. The electron will be taken into the external circuit, will be again combined in the anode for producing the electricity. The other end of the electrode we call as a cathode. So this is the anode. This is cathode. The other end, we are sending oxygen. So you are reducing oxygen. So H plus and O minus will react. Finally, H plus and O minus will react, produces water. So here I am talking about the hydrogen fuel cell. So during the reaction, also it is going to be comes out. So apart from the water, you are going to get the electricity. So there are three products that we are going to receive at the cathode side: heat, water, and electricity. The unreacted, unconverted hydrogen will be again collected back to the recirculation thing. Similarly, oxygen also will be sent it back again to the for the next cycle. Okay. So the hydrogen fuel cell, the electrochemical process in which we are producing electricity, it doesn't create any harmful, I can say, emissions. Doesn't create any harmful emissions. Suppose in automobile, suppose if you want to, I can say, use this fuel cell as a primary, I can say, the energy source, right? So ultimately, you are going to get at the exit water, only water. So then the current generated is going to be used for running the vehicle. Then this is the positive sign, I can say. This is a positive sign, I can say. But in case of water, right? So you need to have a proper design of the anode surface, cathode surface, and then the GDI, gas deficient layer. The design of all the components associated with fuel cell also plays a major role in producing maximum electricity. Then the removal of water is also a big problem in the hydrogen fuel cell. Removal of water, because once the water is formed inside the cathode zone, then you need to expel out the water immediately, or otherwise it's going to create a concept problem called water flooding. Water flooding. So form the water, produce the electricity, water can be, how fast you can able to remove the water from the fuel cell will increase the energy density, I can say, you can say, or current density, you can say, current density is expressed in terms of milliamps per centimeter square. For square centimeter of, I can say, fuel cell surface, how much the current you are going to you are going to produce it, that will decide the type of fuel cell. Based on the type of fuel cell, which fuel cell is going to produce maximum current with respect to the unit surface area. So there are different types of it. So it is like a battery that can be charged while you are drawing power from it. So the best the good can say comparison is you may be using a battery for the inverter in every house. There the energy is stored whenever the power comes from the grid, you know, it is you can able to store it in the battery. Whenever the power from the grid is stopped, you are going to give the power to the need, which is for the applications, the system we are having in the house. Whereas in the fuel cell, it is not a, can say, stored form of energy. You can continuously produce the electricity. So when the fuel is available, you can say how much time I can able to produce the electricity from the fuel cell. That depends on how much the fuel you are going to, how much time you are going to supply the fuel. Suppose you have hydrogen to supply fuel for, I can say, for the power generation for 1 hour, up to 1 hour you can able to produce the electricity. Okay. So it purely depends on the fuel availability. Does it say that it doesn't store the energy? So it is something like similar to the internal combustion engine. You can burn the fuel, produce the chemical energy to heat energy, then convert it to mechanical energy. So how much fuel you are supplying, accordingly that will be converted to mechanical. Similarly here, how much the fuel you are supplying to the anode zone, accordingly due to the electrochemical reaction, then how much energy can be possible from the electrochemical cell, we can say that much amount you can able to produce the electricity. So the fuel cell is a device that generates electricity by a chemical reaction. Every fuel cell has two electrons, one is positive and one negative. called cathode. So normally positive terminal is cathode, anode is a negative terminal. So the single fuel cell consists of an electrolyte and two catalyst coated electrodes. So you have one electrolyte and the two electrodes which are coated with electrodes. We are coated with catalyst. A fuel hydrogen is fed into the anode side. You can see here, where the catalyst separates the hydrogen negatively charged electron from positive charge. So the purpose of the catalyst on the anode is to do the oxidation process where it will produce hydrogen in positive sign as well as electricity, and the reacted product of positive ions will move towards the electrolyte will contain only positive ions. It will be goes to the cathode side, whereas the unreacted hydrogen will be again recycled in the, I can say, the anode side. The negative ions comes out from the catalyst surface of the anode. It goes to the external circuit, again is going to combine in the cathode region. So the electron along with the positive ions from the anode comes through the electrolyte, combined with the oxygen and the negative, I can say, sign, you are going to produce the water. Heat is going to be during, because it's nothing but something like exothermic reaction. The heat will also comes up. That's the reason why the fuel cells are, I can say, rated based on the temperature also. The ambient temperature fuel cell, high temperature fuel cell, and the medium temperature fuel cell, 40 degree, 40 to 80 degree, maybe I can say 100 to 200 degree or 400 to 600 degree, something like this. That depends on how much the reaction, how much the temperature is going to come out during the electrochemical reaction. Okay. So fuel cell, it is the exploded view of the fuel cell. You can see here. It has the assembly to keep the electrolyte, you keep the membrane, and keep the, I can say, the gas diffusion here. Something like you can the sandwiching of the bread, right? Suppose you want to buy sandwich bread, or you want to buy some burger. So it is not only it is having only, I can say, the bread. It has the different vegetables, different cheese materials, right? So similar to that, it is something like a sandwiching of different components. You form a fuel cell assembly. Okay, when you say fuel cell, it's not only having an electrode, anode and cathode, and apart from that, other components also added into the system. Okay, you can say an anode, the catalyst zone, then membrane, then catalyst, cathode. So cathode also, you have to coat the catalyst. Anode also, we need to use the catalyst. There are different catalysts are available, noble or non-metal, I can say green catalysts are available. And ultimately, the purpose of the catalyst to consume only minimum energy to get the positive ions, which can be sent into the cathode via the, I can say, controller. So here the concept mentioned here is that polymer electrode membrane fuel cell. Here the membrane is an Nafion membrane. So it can, the membrane will contain only positive ions, doesn't contain the negative ions. That's why the negative ions are goes away from these, I can say, from the anode, and it will be again coming to the cathode side, which is positive. So it has the electrocatalyst, oral thermically conducting. So the cost depends on the cell temperature. So what is the type of catalyst you are going to use? That depends on the operating temperature of the fuel cell. We go for high temperature, 600 to 800 degree, I can say solid oxide fuel cell. Then the catalyst we are going to use it over the, I can say, the membrane or the anode or cathode to be able to withstand the operating temperature of the fuel cell. So that also need to ensure that there are different catalysis methods are available to find out the operating regime of the catalyst. The best thing is the TGA, thermogravity analysis. Anode is a negative post of fuel cell, contains electrons that are freed from the hydrogen molecule so that they can be used in an external circuit. So there are, don't think that anode or cathode is a smooth surface. The different surface geometries are used for anode or cathode. So that also plays a major role in producing the conversion of hydrogen into H plus an electron. So there are a number of studies are done with modifying the cathode assembly or anode assembly as well as the membrane assembly. And we are not going to discuss about that. We are going to discuss only the basic of the how the fuel cell is producing the electricity. So cathode is the positive post of fuel cell. It's not smooth. Electric channels are there. Conduct electron back from the external circuit, which is coming from the anode, going to be absorbed in the cathode side. Recombine with hydrogen ions and oxygen form water. So ultimately, you are not polluting the environment when you are using hydrogen as a fuel. You are producing heat and electricity along with the water. Water also can be utilized. Suppose the same water you want to use it for in the same maybe stationary fuel cell or I can say automatic fuel cell. Then there's a possibility of taking the electrolysis, breaking the water into hydrogen, then oxygen. Then the hydrogen instead of supplying from the cylinder, you can generate the hydrogen on board from the water generated from the fuels. So you can collect the water, you can by using a small pump, you can send it to the electrolyzer. That is also possible. So electrolytes, there are different electrolytes are generally used. The fuel cell based on the alkalinity, say alkaline fuel cell, acidic fuel cell, phosphoric acid, molten carbonate is a high temperature fuel cell, molten lithium, potassium, then the sodium carbonates or ceramic, something like a solid, I can say. So maybe a mixture of liquid or solid, or sometimes the electrolyte itself is there. High temperature withstanding, I can say, material, probably carbonates and ceramics. So what is the purpose of the catalyst? In such a material that facilitates the reaction of oxygen and hydrogen, oxygen in cathode, hydrogen in the anode. Usually platinum powder very thinly coated on the carbon paper on the glass. So electrode may be any material. You can use carbon as a material or copper or stainless steel or iron, whatever the material you can use it, but the coating over there plays a major role in enhancing the reaction, oxidation as well as the reduction. So this is the chemistry, how the hydrogen is oxidized into hydrogen and electron, how the oxygen is reduced into, I can say, O minus, then it reacts with the hydrogen comes from the anode through the electrolyte. It's going to combine with the oxygen which is the cathode. The electron comes from the external circuit also combined at the cathode. Finally, we are going to get the net reaction. Hydrogen reacts with the oxygen, produces water. The field is oxidized on the cathode side and an oxygen reduced on the cathode. One species of ion are transported from one electrode to the other through the cathode to combine the with counterparts. So you can see here, this is anode, this is the cathode. So water at the outcome is water is also forming. You need to provide a space for allowing the fuel into the anode side. Similarly, you need to provide space for entering the oxygen into the, I can say, cathode side. That's called flow channel, we can say. Before the anode or cathode, we are having the arrangement of the flow channel, which can able to allow the fuel into the anode or cathode. Similarly, we are having the flow channel, which can allow the oxygen into the cathode. So, anode, cathode, electrolyte, then fuel entry, oxidizer entry, then collecting the electron comes from the anode to the cathode. That arrangement is also necessary. Ultimately, whatever may be unreacted, unoxidized, or I can say, the hydrogen is going to be again recycled back into the flow channel. Okay. Similarly, here oxygen can be break down into O minus. Then, if it will not break down, again it can be sent into the input of the oxidizer unit. Then you have to give the provision to absorb the heat because the temperature plays a major role in the fuel cell. So you need to ensure that during the reaction, the temperature increases to 100 or 150 degrees. Immediately you need to cool the fuel cell to the actual temperature. So you need to remove the heat continuously and also need to remove the water which will be formed in the cathode zone continuously. Otherwise, the accumulation of water will lead to reduce the electricity generation in the fuel cell. That is called water flooding. So water flooding is the biggest problem in hydrogen fuel cell. So removal of water accordingly need to go for the design of the I can say the flow paths. Okay. There are different flow paths that people are tried, rectangle, square, hexagonal, honeycomb structure, many things people are tried. It's very difficult to go for fabrication of the particular thing before going for some kind of numerical simulation or computational methods to ensure that how the hydrogen flow or how does the water forming going to be removed continuously. So in that case, you need to select the proper geometry of the flow channel based on the computational analysis. Okay, you model the different geometries and ultimately you need to ensure that for cathode flow geometry or anode flow geometry as well as the water removal, what type of geometry is best suited for getting the best, I can say, good, I can say, electricity out of the square meter of the flow path. So based on the temperature range, I said low temperature fuel cell 25 to 100 degree, medium temperature fuel cell, and high temperature fuel cell, very high temperature fuel cell also available. So based on the classification, the anode material, cathode material, catalyst, whatever over that, and electrolyte material also going to be, because at 1000 degrees you are operating with the normal KOH or maybe I can say any kind of phosphoric acid or I can say Nafion membrane to operate with high temperature fuel cell, it will be melted. So you need to select the right material for anode, cathode as well as the electrolyte and also for I can say gas diffusion source. And also the material what you are going to use is going to be the cathode what you are going to use in the anode and cathode will not be takes part in the reaction, it will only reduce the activation energy and also increase the reaction rate happening in the anode side and cathode side. So it should not take part in the any reaction. According to the type of electrolyte, you may have solid, molten, then non-aqueous or aqueous. According to the physical state of the fuel, you can supply in gaseous state, hydrogen, and then lower hydrocarbons, liquids. Normally, people are using alcohol now, so they are planning to produce the electricity from the different low and low. I can say low carbon alcohol to high carbon alcohols. Then there is solid metals. Primary fuel cell, I can say reactants are passed through the cell only once the products of the reaction is discarded. So this kind of fuel cell is once the hydrogen is sent into that, then the hydrogen is not going to be recovered. So need to the people after this one people start working on it to recover the hydrogen because the energy is also involved. Suppose we are producing hydrogen from the dissociation of water to electrolysis, should not waste the hydrogen. And also oxygen, also you are separating oxygen, hydrogen by using can say membrane, or you are supplying from the cylinder. This is also energy intensive process. So what suppose the conversion of hydrogen to H plus or O to O minus happens in anode and cathode, 90%, that 10% is not going to be converted, but those 10% also you need to recirculate back and convert it in the anode side in terms of hydrogen, oxygen inside of cathode side. Then secondary fuel cell, I can say gas, these are the fuel that generally is secondary fuel cell, hydrogen, liquids and solid. So there are different fuel cells based on the temperature. I said low temperature you have polymer PEM fuel cell, polymer electrolyte membrane fuel cell. Because the membrane is a polymer in nature, the polymer electrolyte membrane. This is all electrolyte, right? Fuel, here we are going to use hydrogen. The methanol fuel cell operating the machine. All know that the boiling point of methanol is about 60 degrees centigrade. Boiling starts at maybe 45 degrees. Maybe the complete evaporation will happen at 80 degrees. So here, what is the problem in I can say methanol fuel cell is it contains carbon, CH3OH. Oxygen also there, then carbon also there. This oxygen and also you are sending through the cathode also. So there is a possibility of producing carbon dioxide. So right. So how to eliminate the carbon dioxide? How to eliminate the carbon dioxide without any reaction in the I can say the cathode side because water is already available. The carbon dioxide will combined with water. The carbonic acid is going to be created. That is going to corrode the fuel cell components. So you need to take up how to recover the carbon, or whether you are going to convert the methanol, you are going to allow the carbon into the cathode side, or you take out the carbon at the anode side and take it from the anode and you are using for some other application, that we need to really work on it. Alkaline fuel cell, 150 degree, the operating temperature. The phosphoric acid fuel cells are 220 degree, I can say. Protonic ceramic fuel cell, the operating temperature 650 degree. And molten carbonate fuel cell, 700 degree. Solid oxide fuel cell, 90. Because when you go for increase in temperature, the energy conversion, then the fuel cell efficiency is going to increase like anything. The energy density in terms of the current density is going to be high when you're going for high temperature. But when you go for high temperature, the cost we are going to invest for, I can say, procuring the different components associated with the fuel cell also increases. So need to compromise with respect to power as well as the cost. So the characteristics of the fuel cell, different fuel cells, low temperature fuel cell. You can able to start the process very quickly because the temperature is maximum you can able to attain is 100 degree. Wide range of cell construction metals are available. Even the waste, I can say the biomass material or the activated carbon, whatever this comes out through the different environment, we can convert that one as an electrode. We can able to withstand also that temperature. Low cost materials we can able to withstand up to 100 degree, right? So we can able to construct the fuel cell with the minimum cost. When you go for the fuel cell, the operating temperature about 100 degree. High temperature fuel cell advantages, fuel flexibility. You can go for various fuels. Then because you can able to go for reforming. Now the water is converted into hydrogen, then it can be used for similarly methane, methanol. So all hydrocarbon or alcohol based, can say fuels can be utilized for high temperature fuel cell. But the environmental perspective and economical perspective, this is going to be lot of research is needed to take care of the emission perspective as well as the economic perspective. Because the temperature increases means the cost of the fuels will also increases. Need to go for because need to disturb high temperature. High temperature, I can say the precious materials can be utilized for the fuel cell coating or I can say the electrodes coating. So it will increase the cost of the fuels. Advantage of hydrogen fuel, fast electrolytic reaction, protons and hydronium ions conduct rapidly across the acidic membranes, very high energy to weight ratio, carbon free, eliminates local CO2 pollution. Disadvantage is because you need to store the hydrogen at a pressure of 350 to 650 bar to bring it to the site or to take it in the to do the process in the even automotive engine side or automotive fuel cell application. So instead of producing the electricity here, you are also consuming the energy to bring the fuel into the fuel cell. Then liquefied, you need to maintain the minus temperature to store the hydrogen in liquid form. So this is also energy intensive process. And safety for handling because it's not going to create any pungent smell like ammonia. So you cannot ensure that the hydrogen leakage is happening or not. So need a hydrogen detector. And also you can see here in terms of the laminar flame velocity is very very high. So when the fire occurs, it's very difficult to control the flame. So safety of handling the hydrogen in the desired application is going to be a challenging task. Because you cannot identify whether the leakage is happening, whether it's happening or not. But that problem is not going to be there when you are dealing with ammonia. Ammonia, even small leakage, you will get a pungent smell. So you can easily identify. Even small 1 ppm leakage happens from the system, you can have to identify. But hydrogen, you need a sensors and also some kind of alarm system to give some kind of input to the system that is a leakage happening. So this is the 50 kilowatt natural gas reformer energy technology. The harness energy technology is available. There they are using natural gas. This is similar to how the ammonia, steam lithium, methane reforming and hammer boost technology concept. So if you want to go for hydrogen fuel cell, you need to supply hydrogen. If you want to go for Other than hydrogen, hydrocarbon or ammonia, or I can say alcohol-based fuel cell, apart from the fuel cell, we need a reforming system also. And ultimately, the fuel cell, we need to supply only hydrogen. So you can give the fuel at any mode, but the input to the fuel cell, you can ensure that the carbon-free the fuel is entering, particularly hydrogen. So ammonia fuel cell, coming to the ammonia fuel cell requires the reforming also. Use ammonia as primary fuel source to generate electricity through electrochemical reactions. Unlike conventional combustion process, fuel cell produce electricity without direct carbon emissions, making them an attractive option for achieving carbon neutral goals. So here, when you're going to use the ammonia at the anode side, I can say you need to dissociate the ammonia, break the ammonia into nitrogen and hydrogen, and nitrogen will be taken out. Hydrogen alone contact the anode zone for producing the H plus and electron minus. Okay. So before the fuel cell assembly, you need a chamber where the reforming of ammonia is going to happen. To reform, to do the endothermic process, to break the ammonia into hydrogen, need to supply the energy. Okay. So the energy may be from the solar or wind or from any kind of renewable energy sources. Then the amount of the energy you are going to spend for producing hydrogen from ammonia is going to be ultimately, I can say, comparatively lower than the conversion method and emission free hydrogen generation. Ammonia is considered as a hydrogen carrier. So in ammonia, if you find out hydrogen content, it's about 17.6% hydrogen by weight. It is released. If you break the ammonia, out of 100%, I can assume that after breaking out, 17.6% hydrogen will be consumed from the ammonia, which is offering a clean and efficient energy conversion process. Then once ammonia breaks down to hydrogen, then other things what I discussed earlier going to be remains here. Okay, so very mild enthalpy of reforming is necessary. Ammonia is a liquid at room temperature around 10 atmosphere. You can compress it to 10 atmosphere. You can able to get the ammonia in liquid form. You can easily carry it. In comparison with 650 atmosphere for hydrogen, it is only we are going to give the energy to compress from ambient to 10 atmosphere. The delta P is about I can say the gas pressure is around 11 atmosphere approximately. So to compress it to 10 atmosphere, it is comparatively for hydrogen compression, it's going to be very less. Power density is comparable to other liquid fuels. Vaporize when we open it, it's going to come to the I can easily vaporize it when you reach to the ambient temperature and pressure. Essentially non-flammable, non-explosive, and I can say one unit of 180 kilowatt hour of electricity from burning 15 gallons of ammonia. That is equivalent to 38 kg. If you are able to burn, I can say if you are able to use the ammonia in fuel cell with 50% efficiency, then you can able to say 38 kg. If you are using it, you can able to produce 180 unit of electricity. It's well established transport and storage infrastructure already in place. As I know that India is now second largest producer of ammonia. So already ammonia, we know the method of producing ammonia. So then bringing ammonia into the fuel cell is not going to be very much complicated when compared with other countries. So externally reformed ammonia. So for the reforming ammonia, there are many methods people are using. So something like the electrolyzer. So you can have electrolyzer or something. You can use it. Different types of electrolyzers are available. For respect to temperature or something, you can use it. So classification of fuel cell, there are two types, direct ammonia fuel cell and indirect fuel cell. In the direct type of fuel cell, you can use ammonia directly, I can say, but the nitrogen, if it is reacts, there's a chance of oxides of nitrogen. Indirect type of ammonia means you are breaking the ammonia into hydrogen, then there is no issue of the other than the water, then nothing is going to be the product of, I can say, the electrochemical reaction. So in order to use the different, I can say, the fuel directly without going for reforming into hydrogen, there are different fuel cells are available, solid oxide fuel cell and alkaline fuel cells. So in the, under solid oxide fuel cells, we have a proton conducting solid oxide fuel cell, oxygen anion conducting solid oxide fuel cell. Alkaline, under alkaline electrolyte, we have anion exchange membrane fuel cell and molten aqueous type of fuel cell. So the simple thing again, we are the same thing. So what is the direct, I can say ammonia fuel cell, the indirect type of fuel cell. So direct type is you can directly use ammonia. So it will be breakdown. There's a possibility that nitrogen will be comes out the same fuel cell itself. Then we will be getting, I can say similarly the oxygen side, the cathode side, you are going to send the oxygen and this thing. The lowest possibility is going to be there in the membrane side. So the reaction going to happen between anode and cathode. So you are going to produce the water. But one thing you must remember during the reaction, there's no possibility of nitrogen or reacts with the oxygen. So that will lead to the very toxic, I can say, emissions. The nitric oxide, if this formation happens, is going to affect the fuel cell assembly. When it is dissociated, ammonia dissociated and anode side, then you can say you are going to produce the hydrogen. 1 mole of ammonia produces 1.5 mole of hydrogen and half mole of nitrogen. If it is completely converted. If it's not completely converted, then you can again send back, recycle it and send back. Similarly, here 0.5 mole of oxygen combined with the electron comes through the anode side, going to produce O2 minus. H2 comes out from the anode through the electrolyte, reacts with O2 minus, which is entering into the electrolyte, forms water. So during the exothermic reaction, apart from the water, heat, as well as the electricity is going to come out, that is going to be taken for the different application. So you can even say the indirect type, we are not sending ammonia into the cathode side. So we are breaking it. So if the ammonia breaking dissociation happens outside of the reactor system, outside of the fuel cell assembly, that is called indirect type. If it is happening, the dissociation happening along with, I can say, the association of hydrogen into electricity, there is nothing but a direct ammonia fuels. But you need to provide high energy to dissociate the ammonia. So maybe you can provide heat or you can provide the electricity, I can say, the power to break this. Electronic material or direct, I can say, ammonia fuel cell. As a high temperature reaction would happen to break the ammonia. So normally the temperature is around more than 600 degrees centigrade. So I can say at 800 degree, and you are going to produce about the power density of 202 milliwatt per centimeter square with 15 micron meter catalyst thickness. So if you go for yttrium stabilized zirconia, it can withstand up to above 1000 degrees centigrade. So whenever you want to go for it's a deformation of the, I can say, reforming of the ammonia, accordingly the temperature of the particular the reforming zone also plays a major role. The material of the reactor as well as the catalyst plays a major role. So accordingly, the high temperature, I can say, stable, I can say, catalyst can stand high temperature, you can select. Then the samarium doped ceria, the power density is about, I can say, 1190 milliwatt per centimeter square. What the power density means is, if you go for, I can say, this kind of catalyst, I can say up to, I can say, 60 degrees centigrade deforming zone, you can able to produce the power, I can say, per unit square centimeter of fuel cell, 1190 milliwatt power can be able to generate. Electron material, nickel or platinum, cathode, I can say, samarium, strontium cobalt oxide, lanthanum, strontium, magnesium oxide. Temperature impact, increasing the temperature, enhance the ammonia dissociation and electrochemical. As I already said, when you go for high temperature fuel cells, then the efficiency, conversion efficiency going to be improved. But as I said, right, you are going to go for a noble materials, right? Platinum, palladium, rhodium, ruthenium, then the zirconia. These are all like even 3 milligrams cost, I can say, very high. So when you go for high temperature, to withstand high temperature, you need to go for preferably noble materials, which can have, there's a major role in converting that ammonia into, I can say, hydrogen, or further conversion of hydrogen into water, followed by heat and electricity. So high temperature fuel cell always in terms of performance percentage is good. In terms of capital cost, right? In terms of the equipment, is going to be power density compared with, I can say, membrane fuel cell or the alkaline or acid fuel cell is going to be comparatively power density, current density. So advantage of, I can say, solid oxide fuel cell, high efficiency in converting ammonia to electricity, and utilization of ammonia eliminates the need for external reforming, potential for integration into green energy systems. High operating temperature, 500 to 1000 degrees, increase the material and system cost. Formation of environmentally harmful nitrogen oxides is also possible. Because ammonia contains nitrogen, in order to form the oxides of nitrogen, you need a temperature. Because the temperature of the reactor is 500 to 1000 degrees, then oxygen is also available. I can say you are providing through the cathode, right? Then if you combine somewhere, there is a possibility of oxides of nitrogen. So we need to find out the method in which eliminate the nitrogen, I can say, before it forms. So thick electrolytes result in high ionic resistance and reduce the efficiency. And environmental concerns, NOx emission due to nitrogen reacting with oxygen at high temperatures. Need for further studies to mitigate environmental impacts. So we go for solid fuel cell performance perspective, good. Economic and environmental perspective, it is going to be a question of. So the current research, people are working on, I can say, direct usage of ammonia in solid fuel cell. I can say, developing thinner electrolytes to reduce the resistance, because we go for high viscous electrolytes, the resistance to pass the positive ions going to be for reaching the particular distance to, I can say, assume that the thickness of the electrolyte is 10 centimeter, maybe I can say 10 centimeter. The electrolyte thickness is higher, maybe it can take maybe 10 seconds to reach the cathode. Suppose we go for the same thickness of the electrolyte with the viscous, lesser viscous, it can reach within 2 seconds. Then ultimately, the formation of water and current will be comparatively higher in case of, I can say, low viscous electrolyte materials. The university performance with alternative fuels like hydrogen. Future directions, challenges are also there. Reduce NOx emissions and steady heat generation control. Because NOx formation is mainly due to nitrogen oxygen availability, temperature of the reaction, as well as the specific heat and the particular zone. Be able to tackle, if you are able to control the 3 parameters to avoid the NOx formation, then it is going to be successful design. Improve low-cost designs for commercial and industrial applications. Optimize operating temperatures and material combinations. Potential applications, integration into transportation. People are there now, they are talking about using ammonia in engines also. There is also challenges are there. Ammonia is highly corrosive in nature and toxic also is there. Naturally, using ammonia in engine, already you are producing 79% of nitrogen from air. Along with that, the nitrogen during the burning, it dissociates further and nitrogen also comes out. It also leads to, I can say, more NOx emission compared to burning the diesel fuel in diesel engine or petrol fuel in petrol engine. So need to take care of that. That's the reason why ammonia utilization in engine, the recovery of, I can say, the problem of is NOx emission, if it is controlled and maybe in the engine itself or in the exhaust itself, it is going to be acceptable. Okay, using decentralized power generation systems, ammonia storage in hydrogen. Why it's called decentralized means, suppose you want to power the particular village where there is no provision to bring the power or you need to deliver the power from the village, then you can create a localized, I can say, power station. You can create it and you can give it to the people living in that particular. It's called decentralized. It's not connected to our grid. So the fuel with respect to the, I can say, different fuels are there, people are using. With respect to the so their energy contents are given with respect to hydrogen and hydrogen in gaseous form. 5,000 psi, that is about divided by 14.5 is nothing but 1 bar. About 15, you will get around, I can say, around 600 bar or something will come. Liquid is about 9, 10 megajoule per liter. In terms of volume, they are given. So after reforming, maybe you can see here, let's say a slight changes in the calorific value. So direct fuel cell comparisons, we can go for direct ammonia, we can go for hydrogen directly, the fuel cell, hydrocarbon, solid oxide fuel. So if you want to use ammonia, you can go for, I can say, either solid oxide fuel cell or PCC. Okay. That based on the, I can say, that quality. Operating temperature 500 to 700 degrees centigrade, then 500 to 750 degrees centigrade, hydrogen 20 to 100, then hydrocarbon 800 to 1000 degrees. That is nothing but the dissociation temperature actually. Because we are using direct ammonia, maybe under temperature is possible, but hydrogen, there's no need to, I can say, maybe I can say at that temperature it can easily react with the anode, maybe the catalyst, we can able to convert it into materials. Can use stainless steel, and here we can go for aluminum or ceramic base for solid oxide fuel cell. Electrocatalyst cost low for direct ammonia, high in case of hydrogen. Then here it is low. There are different electronics materials that they are using. You can say nickel, cobalt, lanthanum, and magnesium. Sorry, manganese. Then this is for hydrogen gas. Electronic materials are platinum, palladium, lithium, or solid oxide fuel cell. I can say the electrocatalyst cost is low. Nickel, cobalt, lanthanum, and manganese they are using. Water product discharge, I can say, at cathode, it will gas stream, at cathode, it will gas stream, at cathode, at anode, dilute stream. So there is a periodic table. So many materials are currently available. If you want to go for, I can say, replacement of the material which has a similar characteristics and the cost is comparatively lower. So from the periodic table, you can select the right catalyst material and you can load it on the either catalyst surface or maybe in the anode surface or on the cathode surface, as well as in the graphene membrane. I can say membrane also you can be able to coat it. So there are based on that only they are selecting the different types of noble materials. There are different noble materials which not explored. Also, according to their cost, we can also try. So different countries they have tried with respect to, I can say, lithium, platinum, iridium, ferrous, nickel, copper, chromium, cobalt, lithium, palladium. They come up with, I can say, what is that in y-axis? So, ammonia?
Ammonia dissociation.
Ammonia dissociation. Okay. So ammonia dissociation going to be higher for the lithium catalyst. Next to that, we have ruthenium. So accordingly, you can see that selection of the catalyst. Suppose, for example, this catalyst is lower. The cost per kg is about, I can say, 5,000 rupees or 10,000 rupees. But buying this catalyst, there's no use at all. Even I can say, you can see that buying 10 grams of the lithium catalyst, give the I can say ammonia decomposition, right? The higher rate, we can think about that one also. So go for optimized, I can say, material, optimize the, I can say, the process in which you can be able to select the catalyst, not only from the catalyst but also the conversion, energy, say, input to the conversion, everything you need to take it into. But you can see here the ammonia, I can say, conversion, ammonia to, I can say, hydrogen or conversion happens with respect to various temperatures. Here it is going to be maximum for this kind. So there is catalytic conversion. Ammonia reacts with the oxygen, produces water and nitrogen. Then we can able to, by going for this reaction, cannot avoid the formation of NOx. So is there any process in which the formation of NOx again reacts with the let's say ammonia? You can able to convert the useless material into the useful material, water and that's also this is after treatment method. When we are using in the engine to reduce the NOx, we are injecting the ammonia, or we can say we are injecting the urea. So that way, the ammonia is converted into nitrogen and water. So you utilize inexpensive base material catalyst. So all the water maybe the research you are doing, find out the new material which is lower cost. So don't immediately go for the noble material. Try to find out and from the periodic table I can say what may be the material we can able to replace the conventional material currently available in the market, either by single catalyst or going for multiple number of catalysts impregnated and metal based catalyst. Then we can able to bring that catalyst very near to the noble catalyst with the minimum cost. Then you are maybe I can say you make it a pattern also, your work may be appreciable. Maybe industry also wants that kind of the I can say material. So different material they have tried and different temperatures, the current density is given. So you can see here voltage correspond to the current density. You can see at high temperature, the current intensity is going to be higher. The conversion efficiency is also going to be higher at high temperature. Right. So ultimately you can see here when you go for a high conversion of I can say hydrogen, 100% conversion of hydrogen from ammonia, better I can say based on the research currently available. The low temperature and medium temperature fuel cells are not suitable. We can go for high temperature fuel cell, preferably solid oxide fuel cell. I'm talking about using ammonia in a fuel cell for producing electricity directly. Suppose we are going for, I can say, hydrogen from the ammonia, then you can go for PEM fuel cell. It's a proven fuel cell, low temperature fuels. So research, you can see here, there are a number of researches going on across our institute and also many places. And we have the I can say, joint collaboration with PhD Tech, Advanced Research Laboratory. Professor Karthikeyan is doing very good research. His fuel cell, PEM fuel cells, is commercialized in Bosch. So we are also I can say jointly work with Karthikeyan in terms of the flow channel design, and which is the channel which can be used for permitting the hydrogen fuel, right? And also to remove the water at the cathode side, we also done some kind of MS research and contact projects also carried out along with Professor Karthikeyan, and we need to define the I can say other than the ammonia formation, we need to find out the suitable application to tackle this ammonia. As we are having the engine facility, we need to either create a fuel cell facility for our students to use the ammonia which is coming out from the process into electricity, or we can be able to use the content what we are having and around, I can say, the places nearby our institute. So these are the references we have used for preparing the PPT, and so thank you so much, and I thank all the scholars, those who are really helping me in preparing this. As we are frankly telling, as we are not having any, I can say, basic research facility in fuel cell, but the colleagues of mine, Professor Samsudin, chemical department, is having a fuel cell facility. As we are in the beginning of, I can say, the producing ammonia, and the applications perspective, we need to really explore it. We have the engine facility, we can able to run it either petrol or diesel, but nearly we need to explore or help from somebody working in fuel cell across the industry as well as from the academic institution to take care of our ammonia fuel which are generated in our laboratory in lab scale. We need kind of support. So we need a joint collaborations for that. We are also currently working. Thank you so much.